Good morning, everyone. Today, we're diving into a fascinating area of health metabolic crosstalk and therapeutic ketosis. We'll explore how different hormones in our bodies work together to manage energy, how these systems can sometimes go awry, and how a metabolic state called ketosis can offer a beneficial bypass for our health. We'll look at the intricate dance between hormones like leptin, insulin, FGF21, and adiponectin, and how they impact everything from our heart to our brain. Let's unravel what we call the metabolic web signal, breakdown, and reset. First, in a healthy state, our bodies maintain a delicate balance, or homeostasis, through precise hormonal communication. Hormones like FGF21 stimulate adiponectin, and leptin signals to our brain that we're full through our insulin pathways. However, this system can break down. Conditions like obesity and chronically high insulin levels disrupt these vital lines of communication. Insulin resistance, for example, can make our brains deaf to leptin's satiety signals, and a lack of adiponectin can lead to the accumulation of harmful fats called ceramides. The good news is we can reset this system. Nutritional ketosis provides a metabolic bypass by shifting our body's primary fuel from sugar to ketones. This change can restore our cells' energy production and reduce inflammation, especially in critical organs like the brain and heart. This approach has key therapeutic applications, especially in conditions such as refractory epilepsy, neurodegenerative diseases like Alzheimer's and Parkinson's, and even heart failure. Now, let's meet some of the key players in this signaling symphony. First, we have FGF21, which acts as the energy expender. It's naturally produced when we fast or are in ketosis, and it helps lower blood sugar and fats. It's important to note that FGF21 needs adiponectin to work effectively. Speaking of adiponectin, it's known as the insulin sensitizer. Secreted by our fat cells, it combats harmful fats and lowers cellular ceramides, helping our bodies use insulin better. Then there's leptin, our satiety signal. This hormone tells our brain about our energy status, signaling when we've had enough to eat and suppressing hunger. Unfortunately, insulin resistance can block this crucial signal. Insulin is our master builder, the hormone responsible for storing energy. But chronic high levels of insulin can actually disrupt the signals from leptin and FGF21. Finally, we have HSL, or hormone-sensitive lipase, the mobilizer. This enzyme breaks down stored fats into fatty acids, which is the very first step in our body's process of making ketones. Let's take a closer look at a critical pathway, the FGF21, adiponectin, and ceramide axis. A study highlighted a key dependency. FGF21, the energy expender, is actually powerless on its own. When we treat the body with FGF21, it stimulates adiponectin secretion, which in turn inhibits the accumulation of harmful ceramides in the liver and blood. This leads to improved insulin sensitivity and better blood sugar control. However, as shown in research, if adiponectin is absent, for instance, in adiponectin knockout mice, FGF21 completely fails to lower glucose or ceramides. This really underscores just how interconnected these systems are, and that adiponectin is absolutely essential for FGF21 to exert its beneficial effects. Next, let's explore the hypothalamic regulation, specifically the crucial insulin-leptin connection in our brains. In a healthy state, both insulin and leptin signals work harmoniously. Leptin, our satiety hormone, relies on a well-functioning insulin signaling pathway to effectively communicate with our brain, helping us feel full and regulate our appetite. However, a major disruption occurs with chronic hyperinsulinemia, meaning consistently high insulin levels. When our brain cells are constantly exposed to high insulin, they can become insulin resistant. Think of it like the neuron becoming deaf to leptin signals. It can no longer hear that important satiety signal, which then perpetuates a cycle of overeating and contributes to obesity. Now, let's identify some of the antagonists, the villains of metabolic dysregulation. First, we have ceramide accumulation. Ceramides are toxic lipids that accumulate in our cell membranes, often from diets high in saturated fats or due to inflammation. They're harmful because they inhibit adiponectin, which we know is crucial for insulin sensitivity. Critically, ceramides also block insulin signaling, leading to widespread insulin resistance throughout the body. Our second antagonist is SOCS3 upregulation. Chronic exposure to high insulin levels triggers an increase in SOX3. This molecule acts as a suppressor, creating a negative feedback loop that physically blocks both insulin and leptin signals. Essentially, it locks our brain in a resistant state, preventing it from properly sensing fullness or managing energy. Let's talk about the metabolic switch, the amazing biochemistry of ketogenesis. This process is triggered by a key hormonal shift: low insulin levels combined with higher glucagon. It begins in our adipose, or fat tissue, where stored fats are broken down into fatty acids. These fatty acids travel to the liver, where they undergo a series of transformations. A crucial enzyme, HMG-CoA synthase, acts as a rate limiter, controlling the speed of ketone production. The end result is that ketones, primarily acetoacetate and beta-hydroxybutyrate, are exported from the liver and become a fantastic fuel source for our brain, heart, and muscles. What's remarkable is that ketones provide even more energy per molecule than glucose, making them a super efficient fuel. For those interested in leveraging these benefits, there are several effective strategies for achieving nutritional ketosis. The classic ketogenic diet, often a 4-to-1 ratio of fat to protein and carbs, is very effective, particularly for conditions like epilepsy, though it can be strict. The MCT diet incorporates medium-chain triglyceride oil. MCTs are more ketogenic per calorie, meaning they convert to ketones more easily, allowing for a bit more flexibility with protein and carbs. Then there's the modified Atkins diet, typically a 1-to-1 fat-to-carb protein ratio with 10-20 grams of carbs daily. This often has better adherence, especially for adults. Lastly, we have exogenous ketones, which are ketone supplements. These come as salts or esters. Ketone salts can have a high salt load and give a lower peak of ketones, while ketone esters are more potent, providing a rapid boost in ketones and can help reduce the liver's glucose output. Let's look at a key therapeutic application for ketosis refractory epilepsy, which refers to seizures that don't respond well to medication. Ketosis offers several powerful mechanisms here. First, there's direct inhibition. A component from MCTs called degenetic acid can actually block specific receptors in the brain called AMPA receptors, preventing an excitatory neurotransmitter called glutamate from binding and reducing seizure activity. Second, ketosis promotes mitochondrial biogenesis. This means it stimulates the creation of new mitochondria, our cells' powerhouses, and enhances antioxidant defenses, reducing cellular stress. Third, it facilitates a neurotransmitter shift. Ketosis helps balance the brain's main excitatory neurotransmitter, glutamate, with its main inhibitory one, GABA, promoting a calming effect. Clinically, ketogenic diets are incredibly effective in severe cases like superrefractory status epilepticus and drug-resistant childhood epilepsy, offering a much-needed lifeline. Moving on to neuroprotection, ketosis can be vital in addressing what we call the brain energy crisis, common in various neurological conditions. Our brains are like hybrid engines. In Alzheimer's disease, particularly affecting the hippocampus, a major problem is glucose hypometabolism or insulin resistance, where brain cells struggle to use glucose for energy. Ketones can bypass this defect, providing an alternative fuel. This efficacy is often higher in those without a specific genetic marker, ApoE4. For Parkinson's disease, which impacts the substantia nigra, the issue often involves a deficiency in mitochondrial complex I, hindering energy production. Here, ketones, specifically beta-hydroxybutyrate, can bypass this damaged complex, rescuing brain cell respiration. Finally, in multiple sclerosis affecting the white matter, ketones offer anti-inflammatory effects that can reduce neuroaxonal damage and help preserve crucial nerve fibers. Essentially, when the brain's primary glucose pathway is compromised, ketones provide a powerful and effective alternative fuel source. Let's shift our focus to cardiovascular health and heart failure. In a failing heart, there's often a significant energy deficit. The heart loses its ability to efficiently burn fatty acids for fuel and instead reverts to a less efficient process called glycolysis, which uses sugar. This energy shortfall contributes to the heart's decline. However, our hearts are unique. They consume more ketones per unit mass than any other organ. A ketone-fueled heart can operate with superfuel, exhibiting high hydraulic efficiency. This means ketones provide a more efficient and powerful energy source for the heart muscle. It's also interesting to note the synergy here. Certain medications, like SGLT2 inhibitors, work partly by stimulating a mild state of ketosis, underscoring the benefits of ketones for cardiac function. Finally, let's discuss future directions, precision nutrition, and safety. Understanding these intricate molecular interactions allows us to move beyond generic dieting to highly targeted metabolic therapies. This involves considering several factors. First, genetics play a crucial role. It's not a one-size-fits-all approach. Genetic factors, such as your ApoE status, can significantly dictate how effective ketogenic interventions might be for conditions like neurodegeneration. Second, the microbiome, the vast community of bacteria in our gut, is also impacted. Ketogenic diets can alter gut flora, and beneficial changes like the enrichment of Akkermansia bacteria have been linked to seizure protection. Probiotics may even be needed to prevent certain liver issues. And critically, safety monitoring is essential for long-term adherence. This includes checking for potential side effects such as kidney stones, growth retardation in children, cardiac fibrosis, and certain nutrient deficiencies like selenium. Always consult with your healthcare provider to ensure these therapies are safe and appropriate for your individual health needs.